Statistical interaction describes a relationship between two variables that is dependent upon or moderated by a third variable.
For instance, do you prefer ketchup or soy sauce? Obviously, your answer depends on what food you're eating. If you're eating sushi, you probably prefer soy sauce. And if you're having a burger and fries, you're probably going to want ketchup.
In this case, the third variable is referred to as the moderating variable, or simply the moderator. The effect of a moderating variable is often characterized statistically as an interaction, that is, a third variable that affects the direction and/or strength of the relation between your explanatory, or x variable, and your response, or y variable. What if the population we're studying has different subgroups? Could it be that, like the soy sauce ketchup example, different subgroups could have a moderating effect on our association of interest?
To explore this idea, we're going to use a hypothetical study and some made-up data. In our imaginary study, we're looking at two diets and their effects on weight loss. Diet A is a low-carbohydrate plan. Diet B is a low-fat plan. Our hypothetical study also recorded data on which exercise program participants chose, cardiovascular exercise or weight training.
Our variables of interest are diet and weight loss. We've added this third variable, exercise plan, to help us understand moderation or statistical interaction. So what's the association between diet plan A and B, our explanatory variable, and weight loss, our quantitative response variable? This table shows our hypothetical data showing diet, weight loss, and exercise plan. Since we have a categorical explanatory variable, diet plan A or B, and a quantitative response variable, that is, weight loss, we will of course need to use analysis of variance to evaluate the association. This Model R syntax should look familiar to you. Inside the AOV function, we provide first a formula of the form quantitative response variable tilde categorical explanatory variable, and second, the name of the data set so that R knows where to find these variables. We store the results in a new workspace object, and to look at the overall ANOVA result, we run a summary function of that object. Finally, in order to help interpret the results of the ANOVA, we use the by command to calculate the group means of the response variable for every level of the explanatory variable. In this example, the syntax would look like this. The resulting output for this analysis is shown here. As you can see, we're testing the association between diet A and B and weight loss. There are 40 observations in the data set. The F value is 12, and it's associated with a significant p-value, that is, a p-value less than 0.05. While this tells us that there's a significant association between diet type and weight loss, to understand that association, we need to look at the output generated by the by function. Here we see that the average 1-month weight loss for diet A is about 14.7 pounds, and that the average 1-month weight loss for diet B is about 9.3 pounds. So, in conjunction with a significant p-value, we can say that diet plan A is associated with significantly greater weight loss than diet plan B. Here we show the finding graphically as a bar chart with diet, the explanatory variable, on the x-axis, and the mean weight loss, our response variable, on the y-axis. But what about our third variable, exercise program? Would we get the same results in terms of the association between diet and weight loss for those participants using cardio and those participants using weight training? In statistics, moderation occurs when the relationship between two variables depends on a third variable. In this case, the third variable is referred to as the moderating variable, or simply the moderator. The effect of the moderating variable is often characterized statistically as an interaction, that is, a third variable that affects the direction and/or strength of the relation between your explanatory and response variable. So, does type of exercise program affect the direction or strength of the relationship between diet and weight loss? The standard way of asking this question in the context of analysis of variance is to move to the use of a two-way or two-factor analysis of variance rather than the one-way or one-factor ANOVA that we've been using. Instead, we're going to take a less standard approach that can be consistently used across each of the inferential tools. That is ANOVA, chi-square, and Pearson correlation. In each of these contexts, we're actually going to be asking the question, is our explanatory variable associated with our response variable for each population subgroup or each level of our third variable? That is, our diet type and weight loss associated for those doing the cardio exercise program, and our diet and weight loss associated for those using the weight training program. To accomplish this, we're going to run two separate ANOVAs, one for each level of the third variable, that is, for each exercise program. Syntax to be added to your code is circled here in red. This by function tells R to run the two commands in the list, which are the analysis of variance and the summary function, and to output the results for each level of the third variable. Function X is basically a placeholder in R code that says you're going to perform whatever functions follow. The X is important because in the functions that follow it, the dataset is referred to as X. This is because in the first line, you're setting up X to be the dataset for just the observations of each level of the third variable in turn. By adding the list function, you're telling R to run multiple functions inside the list function for each level of the third variable. The specific syntax for the diet and exercise example is shown here. Notice that you don't use the name of your dataset anywhere but in the two spots on the first line of this function. In R, when we load this example diet and exercise dataset and run the analysis of variance, we'll see the following results. The output is in order of the alphabetical levels of the third variable. The ANOVA table examining the relationship between diet and weight loss for those in the cardio exercise group shows a large F value and a significant associated p-value. If we use the F table command along with the by statement, we can get a more nicely formatted version of the means for the diets within each type of weight loss. When we examine the means table, we see that for those involved in the cardio exercise program, diet A is associated with greater weight loss, 20.5 pounds on average, while the weight loss associated with diet B is 7.1 pounds on average.
The association between diet and weight loss for those involved in the weight training exercise program is also significant. It has a large F value. However, the means show that the association is in the opposite direction. For those involved in weight training, diet B is associated with greater weight loss, 11.5 pounds, compared to diet A, only 8.8 pounds.
Here, these results are shown graphically. As you can see, the relationship between diet and weight loss depends on which exercise program is being used. When using cardio, diet A is significantly better for weight loss than diet B. When using weights, diet B is significantly better for weight loss than diet A. Thus, we can say there's a significant statistical interaction between the variables diet and weight loss, and the type of exercise, our third variable, moderates the association between diet and weight loss.
Suppose that we did not evaluate exercise as a possible moderator and instead focused only on the association between diet and weight loss for the entire population. Based on this graph, obviously, we would have incorrectly concluded that diet A is better than diet B. As we now know, that is only true if we're looking at the cardio group.
Now let's evaluate third variables as potential moderators in the context of the chi-squared tests of independence. For this, we're going to return to our original R program using the NESARC data and asking the question, is smoking associated with nicotine dependence? We're going to create another smoking variable for this purpose, reflecting how many cigarettes each young adult smoker smokes per day. 3 indicates those smoking 1 to 5 cigarettes per day. 8 indicates 6 to 10 cigarettes per day. 13 indicates 11 to 15 cigarettes per day. 18 indicates 16 to 20 cigarettes per day. And 37 indicates greater than 20 cigarettes per day. 0 will indicate non-daily smokers. Now we're going to request a chi-square test of independence, examining the association between nicotine dependence in the past 12 months and this new smoking variable called USQuan. We're calling our new workspace object in which we're going to store the results of the chi-square test nd14.chisq. And remember, the function prop.table is given a table as its first argument and then the number 2 as its second argument to indicate that you want to obtain column percentages. As we can see from the large chi-square value and significant p-value, smoking quantity and nicotine dependence are significantly associated. In examining the column percents here of each smoking group with nicotine dependence, we see generally higher rates of nicotine dependence among groups that smoke more. So among non-daily smokers, only 25% are nicotine dependent. Among those smoking 1 to 5 cigarettes per day, indicated by a code of 3, nearly 50% meet criteria for nicotine dependence. Those numbers increase with higher levels of smoking. To graph these proportions with code, we use the following. Let's review what this code is telling R. First, we create a new data subset, which we're calling ND-USQuan just for graphing. This temporary data subset includes only the unique identifier, ID_num, and our 2 current variables, tab12MDX and USQuan. Next, we remove all the NAs in the new plotting data set. After that, we make the response variable, tab12MDX, into type numeric. But remember that this is just for the purpose of creating a proportion in the plot. In most other cases, tab12MDX should be treated as a categorical variable. Finally, the last command generates the graph by specifying the data set for plotting and the type of graph we want, which is the proportion of nicotine dependence on the y-axis within each category of usual smoking quantity on the x-axis. And this gives us the graphic representation of this positive linear relationship. As smoking quantity increases, so does the proportion of individuals with nicotine dependence. This finding is accurate with regard to the larger population of young adult smokers. But might a third variable moderate the relationship between smoking quantity and nicotine? Put another way, might there be a statistical interaction between a third variable and smoking behavior in predicting our response variable, nicotine dependence? We're going to evaluate major depressive disorder as the third variable. Our question will be, does major depression affect either the strength or the direction of the relationship between smoking and nicotine dependence? Put another way, might a third variable moderate the relationship between smoking and nicotine dependence? Is smoking related to nicotine dependence for each level of this third variable? That is, for those with major depression and for those without major depression. In order to investigate the possibility of a third variable moderating the relationship between 2 other variables, you use the following code in R. It's similar to the code we used for the ANOVA test with the exercise and diet example dataset. To review, include the by function to tell R to run a chi-square test for each level of the third variable separately. Function x is basically a placeholder in R code that says you're going to perform whatever functions follow. The x is important because in the functions that follow it, the dataset is referred to as x. This is because in the first line, you're setting up x to be the dataset for just the observations of each level of the third variable in turn. By adding the list function, you're telling R to run multiple functions inside the list function for each level of the third variable. And remember, the function prop.table is given a table as its first argument and then the number 2 as its second argument to indicate that you want to obtain column percentages. Here's the specific syntax to use to see if our third variable, major depression, moderates the relationship between smoking our categorical explanatory variable, and nicotine dependence, our categorical response variable. This code looks more complex than the chi-square code without the third variable because we're repeating the chi-square command in each line rather than storing our results in objects. This code performs 3 separate procedures for each level of major DEP life. First, it runs the chi-square test between nicotine dependence and smoking quantity. Second, it produces the cross-tablature table between nicotine dependence and smoking quantity. And third, it calculates the column percentages for this table, which tells us the percentage of those with nicotine dependence within each category of smoking quantity. After we add this code to our R program and run it, R gives us these results. You can see the tabulation table looking at usual quantity by tobacco dependence in the past 12 months. First, for major depression equal to 0, which is those without major depression, the chi-square value is large and the p-value is quite small. In addition, the column percents reveal what seems to be a positive linear relationship, with percentages of nicotine dependence increasing between lower levels of smoking and higher levels of smoking. So we can say that this is a statistically significant relationship for those without major depression. For those with major depression, we find a large chi-square value and small p-value, which is statistically significant. These column percents also reveal what seems to be a positive linear relationship, with percentages of nicotine dependence increasing between lower levels of smoking and higher levels of smoking. Although those with major depression show higher rates of nicotine dependence at every level of smoking quantity. In this case, we would say a diagnosis of major depression does not moderate the relationship between smoking and nicotine dependence. For both young adult smokers with major depression and those without, higher levels of smoking behavior is associated with higher rates of nicotine dependence. So now, let's test for moderation within the context of our final inferential test, the correlation coefficient. You might remember this scatter plot and correlation based on the Gapminder data between rate of urban dwellers in each country and the internet use rate. We found that this was a significant association with a correlation of 0.61. But might this relationship, this correlation between urban rate and internet use rate differ based on countries with different income levels?
To explore this question, we've created a third variable called income group, which is categorical. For this new variable, the income per person variable, which is quantitative, was categorized as a high income country given a value of 3, a moderate income country given a value of 2, and a low income country given a value of 1.
The adjustments we make with the correlation coefficient are very similar to the adjustments we made to our ANOVA syntax and our chi-square syntax when testing moderation. We begin by creating the third variable, a new categorical variable called income group. We tell R to run the correlation for each income group. We use the by function around the syntax we previously learned to run for correlation. Here, the correlation test between urban rate and internet use rate is the only function that needs to be performed at each level of the third variable, income group. When we examine the correlation coefficients between urban rate and internet use rate for each of the income groups, we find the following. For Group 1, the low income group, the correlation between urban rate and internet use rate is 0.116 and the p-value is not significant. For Group 2, the moderate income countries, the association between internet use rate and urban rate is 0.329, with a significant p-value at 0.001. And finally, among high income countries, Group 3, the correlation coefficient is 0.0895, again with a large p-value, suggesting that the association between urban rate and internet use rate is not significant for high income countries. When we map these findings onto the associated scatter plots for each income group, we're able to better visualize the significant and non-significant relationships. Estimating a line of best fit within each scatterplot shows the positive association between urban rate and internet use rate among the moderate income countries, and almost no relationship between those two variables in both the low income and high income countries. Asking questions about statistical interactions can be an interesting way to explore your data and your associations of interest. This is not difficult to do using the skills you've acquired thus far. There are more advanced topics that we can cover here, such as multivariate techniques, that can be very powerful. But even without these techniques, we can still use bivariate inferential tools of ANOVA, chi-square, and correlation to describe our sample, make inferences about the larger population, and really begin to understand what relationships these associations hold under what conditions or at what levels of our third variable. Now that we've found associations, can we assume that association implies causation? We'll answer that question soon.